Welcome to MagNet. Just to give you an idea of the format for today, we are going to have 25-30 minutes presentation. So during that, please keep your microphone mute and turn off the video if your connection is poor. After that, we will have 10-15 minutes of question and discussion. So if you want, you can raise your hand or test the question on the chat, and we will read it out loud for you. And after that, also out of recording, we will turn off the record, and we will have a few time for catch up if you are interested. And I'm pleased to present Cathy Constable today in MagNet. With the title of Weather in Earth's Core, Defining and Categorizing Geomagnetic Excursion and Reversal. So thank you so much, Cathy, and the floor is yours.
Okay, great. Thanks everybody for being here. I want to talk today about some things that Matty Morsfeld and I have been working on for several years, and we're finally getting around to writing up as a paper, and it seemed like this would be a good time to share it with the world at large. And our idea is to think of the state of the internal magnetic field as being like a weather system, and the motivation for that can come from the idea that both things involve the Navier-Stokes equation for Newton's second law, and that there are thoughts that when you get an excursion or a reversal, we could think of that as being a lot like a magnetic storm, and maybe characterize it in the same way as one would something like a hurricane or an unusual weather event. So that's what we're doing. And in the same way, we think of the external magnetic field, as you see here, as being represented by space weather. We're thinking of the internal magnetic field as being represented by core weather. So I wanted to tell you a little bit about how that has been working for us. So let's start. I don't need to tell this audience, I don't think, what a magnetic field reversal is, but just a reminder here that we've been studying them for over a century now, and we still don't really know that much about them in many ways because of the difficulty in getting good records. So the reverse field obviously has the opposite polarity to what we see today. But if we want to define a transitional or an excursional field state, things become a little more complicated, because in an excursion, the field departs from the dominantly dipolar structure. And you might say that one definition of a transitional field or an excursional field is a virtual geomagnetic pole latitude. So that when magnetic north locally moves to a latitude of less than 45 degrees. Another categorization could be looking at low field strengths. So if you think of the virtual dipole moment as being less than half that of the current field, that would be another way of categorizing it. We can also use a criterion that Sanya Panofska introduced in 2017 that called the Paleosecular Variation Index, that combines both direction and intensity in a single attribute for the magnetic field. And what I want to talk about here is a slight modification of that. The PSV index, as originally defined, looked at something that was a local or regional measure of the field. And here we're going to use the level of a modified global PSV index, which has, you'll note, has a little d in here, to define the state of the field as a function of time, and use its peak value to categorize geomagnetic excursions and reversals. And the D in here, you'll see later on, comes from the fact that we're only going to consider the dipole part of a field based on a paleomagnetic field model. So here is a nice picture of, I just need to get rid of this bar here. Yes, okay. Here's a representation of the magnetic field during the Matuyama-Brunhes reversal, so the most recent reversal. And this is a global model for the interval 900 to 700,000 years that was published by Magoo et al. In 2023. And what I want to emphasize here is here are the records that go into it, or the locations of the records. There are some volcanic records which provide the intensity scaling. And then there are sediment records that are distributed all over the surface of the Earth. And you see here the results from 3 different models. The most recent one is GGFMB that was published in 23. And then some others in here, some earlier models, which are based on a much less comprehensive data set or sets. And what you see in here is that when you get a reversal, as we're moving forward in time from left to right, you see that there is a decrease in the dipole moment here, followed by a rebound and recovery. And if we look at the pole latitude, it goes gradually puttering along here, going up and down, looking a little bit excursional perhaps here. And then there's a fairly rapid directional transition over here when we come to the normal polarity Brunhes epoch over here. And if we look at the paleosecular variation index, which is a combination of the dipole moment and the pole latitude, what you see in here is that it basically grows very large during the course of a reversal, and then it recovers afterwards. And we had suggested that a threshold of 0.5 for this PSV index was the level at which the field became excursional. And if you look down here, then it's dropping down to 0.3. And you see that there are some differences in these records depending on the field model. I think that the most recent one is obviously the most reliable because it has more records. And you also see that there's this thing called the PI stack in here, which is basically an average of this index over the records that went into the field model itself. Okay, so can I go forward? That would be nice. Oh, there we go. Okay, so this is just a reminder that when we look at of what a virtual geomagnetic pole is, we take a declination and inclination record in local coordinates and we transform it into a virtual geomagnetic pole, which is the equivalent dipole location and magnitude that would produce the direction and intensity that we measure locally. So when we're looking at the paleosecular variation index, we can get a global view of what's going on at a single time, rather than the time series that I just showed you. And when we do that, what we're doing is we're combining the co-latitude of the virtual geomagnetic pole, so the deviation from the geographic axis. And this is a picture from the modern field, actually from a swarm initial field model. And you see that the place where the pole departs most from the geographic axis is in the southern hemisphere, and that's strongly influenced by the South Atlantic anomaly and the low intensity that we have in the southern hemisphere. If we look at the virtual dipole moment, we see the same sort of picture, but a different geographic spread. And if we combine these two to calculate the paleosecular variation index, we get this picture that you see down here, where we're basically looking at the normalized departure of the co-latitude over the deviation of the magnetic moment from this value m0, which is can be taken as today's dipole moment or the average over a long time period. And the proposed definition of an excursion would be that this should be larger than 0.5. So if you look at this modern field, you see that it's actually rather small. The largest values in the southern hemisphere are less than 0.3. And there's nothing particularly remarkable about today's field, which is sort of fairly common knowledge from what we know from modern observations. So now what I want to do is to say, instead of looking at this regional value for the paleosecular variation index, we want to look at a global version, which is just based on the dipole moment and the tilt of the dipole in the field at an instant in time. So I'm defining this global PSV index here, which has a subscript D for dipole, which is based on the dipole co-latitude here and the actual dipole moment, which is something that we know when we have a full paleomagnetic field model. And again, we have this proposed definition of an excursion that it's occurring when the value of this modified index is larger than 0.5. So we wanted to use this as a mechanism for defining a basic state for what the magnetic field looks like over as a function of time. And one thing I wanted to point out at this point is, why do we want to do, we're going to do this using a numerical dynamo simulation. And one of the reasons for doing that is because there's so much that we don't know about excursions and reversals from paleomagnetic records. For example, we don't really have a definition of the length of a reversal. Comparisons from different locations can be difficult. We don't have a mechanism for distinguishing between excursions and reversals until after they have finished, and that presupposes that we can get a complete record of what's going on. We don't know where they start, and we don't know what their geographic evolution is. So what we're going to do is in this work, what we're doing is we're looking at the evolution of the dipole moment, the pole latitude, and this modified global paleosecular variation index. And we're going to look at that in a situation where we do know exactly we know well what's going on, and that's a very long numerical geodynamo simulation. So we're defining a framework that's going to distinguish levels of this index, and that's going to correspond to a state of the field that tells you what the field looks like at any instant in time. And then peak values associated with events like which are basically excursions or reversals. And we're going to describe peak values that describe categories of events. So we're saying if you get a peak value that's large, then the category of the event is going to be larger too. And this numerical simulation that we're going to look at is 140 million years long. This gives good global statistics. And we'll also see that reversals and excursions are dominated by dipole decay, followed by changes in the dipole latitude. So the dipole decay is the field strength, and the latitude is the direction going unstable at some point when the dipole decay has proceeded far enough. Both of these give you increases in the index, and we're going to define levels to indicate the state of the field, categories to describe the severity of the events. And as a result of this, we're thinking of excursions and reversals as a form of weather in the core. Okay. So what is this numerical simulation all about? What does it look like? It's a simulation that was produced by the Grenoble group, by Nat Schaefer, Alex Fournier, and Thomas Castille. It was made with the X-shells code, and there are a few details of the non-dimensional numbers here. And what you see here is that this is actually 1/10 of the simulation, so this is like 14 million years in here. And you see the dipole moment is changing polarity. There are excursions in here where it doesn't stabilize in the opposite polarity. And we can look at the pole latitude in here, where you see these brief excursions followed by recovery and so on. And this is the log of the PSV index that we use in here. And you see that it's somewhere a little bit lower than -1 in here. So just to note that this is a simulation that's already been studied by Kyle Goetz, and he provided details of a largely favorable comparison with the magnetic field using the Christensen criteria and Courtney-Spray and et al.'s criteria from 29 for the past 10 million years. And I would say the notable difference from what we know about the magnetic field is that there seems to be less time spent at transitional latitudes than in the 0 to 10 million year old data. Okay, so this is what the entire simulation looks like. I won't dwell on that. We'll go on to the next thing. And what we did was we took all of these observations and we said, let's calculate what the value of this index is and label the state of the magnetic field at any instant in time with a level. And we said that if the level of the index, if the value of the index is less than 0.5, it's normal. From 0.5 to 3, it's level 1. From 3 to 15, it's level 2. And If it's bigger than 15, then it's level 3. And what you see on the right here is a plot of pole latitude on the vertical axis against the dipole moment from this simulation. And you see that almost 97% of the time, the field is in what we would call a normal state. It's at level 1, 2.2% of the time, level 2, 0.4% of the time, and level 3, not much at all. Okay, so we thought this was a good place to start, where we're labeling things with levels. And then we looked at what happens if the field is at a particular level. What's it likely to do next? And that's what you see in this transition matrix here, where we're looking at what happens at a 43-year time step from one position to the next. So if you're in the normal state here, then 99.9% of the time, the next step is going to still leave you in a normal state. 0.1% of the time, you will move into a level 1 state. And we call that a warming up. So what you see over here, because the field is getting greater departure from what we think of as normal. And if you're in the state 1, then you can go from state 1 to state 2, 2.8% of the time with this step, and so on. So this is basically a warming up. But then it could also cool down. And if you are at level 1, then 6% of the time it's likely to cool down. So we can think of these as transitions that are showing us how the field is getting more excited or less excited as a function of a step in time. Okay, so that's a level. Now, when we want to think of an index event, we have to have some sort of definition of what's happening. And we have again adopted here the idea that an event starts when this index goes above 0.5. And then it might drop below 0.5, but if it goes back up again and down again, we would think of this as all being part of the same event, not two events. And so we chose as a criterion for the end of an event when the index has returned to the average value. Okay, so this is an end of event threshold. And you see that we would think of this gray area as being the event, and this gray area over here would be the event, which you might otherwise think of as being 1, 2, 3, or 4 events. And you might note that if you've been listening to hurricane forecasts lately, that hurricanes can go from being category 1 to 2 and 3 and down to 2 and back up to 3. That's not what we're thinking about here in terms of levels. We're thinking that the level can go up or down during the course of an event, and that's all part of the same event. Okay, and the time between the start and the end defines the duration. And this event corresponds to a time during which the field is active. So then we define the category of an event as the maximum level that's reached during the event. Okay, it's a reversal if the sign of the axial dipole is opposite at the beginning and end of the event. Otherwise, it's an excursion. That's what our definition is. Okay, so how do we pick the end of the event threshold? We choose it as being when the index returns to the value of the average over the whole state. And this is basically showing you that we're choosing a level when it's going, it doesn't really matter whether we use in this case the median or the mean of the PSV index. In this case, you get to the same value, but it has to return below that value for the end of the event. Okay. Then the category of an event is the maximum level that we encounter during an event. And in this simulation, there are a lot. There are 1,229. We count 881 of those as being category 1, and smaller numbers being cat 2 and cat 3. And you see that in this histogram here. If we look at the number of reversals, where the polarity actually changes, that's 129. So there are a lot more events than there are actual reversals, almost by a factor of 10. Just here's a comparison that Kyle Gertz looked at this same simulation and was looking at events in the context of low dipole events. And in that case, there were fewer numbers of events, but roughly the same number of reversals. That was not based on any directional information. So a few things to think about. The event duration. What we did was we split the events by category, and it seems that a higher category implies a longer event. So here's the event duration and the relative number that occur as a function of event duration. You see category 1 is the largest number and category 3 is the smallest number, but it's also a longer duration version. Whoops. And on the right here, what we did was we looked at, it turns out that you can get a reversal at any category of an event. And we looked at the distinction between category 2 and category 3 with and without reversals. There weren't enough of category 1 to do this. And what you see is that there's not really a definitive distinction between what we see in category 2 here for reversing or for non-reversing and reversing events, which are the orange lines in here. And in cat 3 for the reversing and non-reversing events, there's not a definitive distinction between the two. So here are a few examples showing you the details of the categorization. And we're going to start with events with reversals across all categories. Here's a cat 1 event, so that's the lowest category that's a departure from normal. And you see that this does actually lead to a reversal. So the dipole moment's coming along here, it goes down, it gets low. The blue line marks when you have it got into category 1, and then it's moving along and eventually recovers. This is the pole latitude, and this is the index plotted on a log scale here. Okay, and when we look at the level in here, we see that at time 0, it goes into to level 1, it goes along, it drops down again, it comes back up, it drops down, and then we go on from there. So this is a cat 1 event that actually leads to a reversal. We can have a cat 2 event, which leads to has a higher maximum level down here, and that also has a reversal. Starts out down here, it's normal, it wanders around in dipole moment versus pole latitude space, and after a messy period in here, it comes out at it starts here, and then it's going from normal polarity to reverse polarity in here. Starts here, goes down, then has a very messy period in here before it recovers and gets to the end down here. Okay, cat 3. And what you see about cat 3 is that it's taking longer and it's getting messier in the process in this yellow track, starting here. A lot of confusion about where it wants to go in pole dipole moment space, and then comes back up here at the other end. And you see that the level is going up to level 1, it's dropping down, and so on. It goes up to level 2, drops all the way down to 0, comes back up, goes up to 3, and then eventually returns to something normal at the end. Okay, so these are all reversal events, but we could have events without reversals across all these different categories. And this is a cat 1 event that has no reversal. It starts up here in the normal polarity. Sorry, it starts here and ends up here, okay? And what you'll see is, so it's going from cat 1, it goes down, goes up, goes down, goes up, and eventually it's over. Okay, cat 2 event, no reversal, is more exciting. It actually goes into the pole latitude, goes into the southern hemisphere here, but then it returns to the northern hemisphere. And so this would be what we would categorize as call an excursion with of category 2. So it's more noisy or more active than a cat 1 excursion would be. And a cat 3 event with no reversal, here's another one where it really looks as though things are getting very active in here, and things go all the way into the southern hemisphere at southern latitudes down here. Sorry, it starts in the southern hemisphere, goes all the way to northern latitudes down here, and then returns to the same hemisphere that it started in. But in the meantime, it has gone as far as level 2 in terms of the activity. And lastly, this is a, sorry, did I miss cat 2? No, okay. So that was cat 3. And then we can look at a compilation of all the things that we see in terms of the evolution of the dipole moment, the pole latitude, and the index for the various categories. So here we are in cat 1, and you see that something is coming down. There's a fairly rapid decrease in dipole moment and a rather slow recovery. In cat 2, you see something that looks rather similar, but the recovery is taking longer. And that's consistent with the idea that higher category events are generally longer than lower category ones, and even more so in cat 3 with the dipole moment. And if we look at the PSV index, we see a broadly similar picture. What you'll see is that the color scales, so the white lines in here are representing the 5 and 95% confidence limits for this, basically for this histogram of events. Okay, let's go back to the geomagnetic field as opposed to a simulation. And what we're going to do is we're going to look at these two paleo field models, the GGFMB that I showed you earlier, and also LS mod 0.2, which is a model from Corta et al. That was produced over the Laschamp excursion from 50 to 30,000 years ago. So here's the Brunhes-Matuyama. It turns out it's a cat 2 reversal event. What you see here's 900,000 years ago, here's 700,000 years ago. It's moving along. The dipole moment drops, goes very low, comes back up eventually. And what you see in here is something that's a little bit different from what we saw in the simulation, in that the decay is more gradual and the recovery is rapid. So there's this sort of asymmetry in the growth and decay that's opposite to what we see in the actuals in the simulation. And if we look at the dipole moment here as a function of pole latitude, here we are in the Matuyama is where we start, and it migrates, hangs around in here for a long time, moves into category 1, then into category 2, never reaches category 3, and then comes back up. And you see that here in the level as well. What about the Laschamp? The Laschamp, it turns out, is also a category 2, and that's because it reaches a level 2 on the basis of this index. You see this coming along here, and it's coming up to here, and it reaches level 2 in there. You see here, it's starting in the northern hemisphere, migrating southwards, coming down, coming back up, and returning to the northern hemisphere again. So this is an example of how it doesn't really seem that we see any distinction between excursions and reversals on the basis of this category. It really does seem that the only distinction is actually between the end state versus the starting state. So that's bringing me to the end. I hope I haven't used up too much time in here. The idea of categorizing the weather in the core is something that I think is a good link into a more general perspective of the Earth's electromagnetic environment. We're looking in here, this is the power spectrum of field variation, dipole field variations. And in the internal part of the field, we're looking at excursions and paleosecular variation. And it seems that there's really not any major distinction between what we see in excursions and reversal rate. There's not necessarily a trigger, but part of a natural evolution. And if we were wanting to extend this analogy, I think there's a lot more that we can do. We can look at this from a regional level to understand how excursions get started and how they evolve over time. Is there a particular point where they start and evolve to? Using this index as a measure of the start and finish and length duration of the reversal. The other thing I think that's interesting in terms of this analogy with weather in the core is that in the long term, we could think of the evolution of the geodynamo, which is basically the thermal evolution of the Earth, as a kind of idea of climate change. Then we could think about how this core climate change is basically potentially influencing reversal rate and field strength. Even though those links between field intensity and reversal rate have been really quite surprisingly difficult to establish, this provides a mechanism for actually thinking about how to study that. So I think I'll leave it there, and thank you. And if you're interested in more, we hope this will come out in GJI soon. It's also, I wanted to mention that in looking at regional variations in the PSB index, there's a paper by Stephen Mason and others that came out earlier this year.
Thank you so much, Cathy, for your nice presentation, and I will ask for a big applause. And if anyone want to make any question, you can raise your hand or text in the chat. Andy, if you want to, you can open your microphone and ask.
Oh, and show himself too.
Yes, I've turned myself on. Hi, fantastic talk, Cathy. Really enjoyed that. Just a question about your very final comments there. So are you suggesting that about climate change of the core, which is something I've kind of like to think about as well. So are you suggesting that then this climate change just happens by itself? Because when I think of climate change, normal climate change, it's externally forced, right? It's anthropogenic, or it's it's Milankovitch cycles, orbitally forced. And in this case, it seems to me there's a very obvious forcing candidate, which is mantle convection on these timescales of tens and hundreds of millions of years.
I guess that all depends on whether you think of the mantle as being external or internal to the core. Yeah, I'm not suggesting that there's an external trigger to this. I think I'm thinking of the climate change as being the long-term evolution of the Earth. And, if you look at this power spectrum that I put up here, what we see in here, there's a kind of average reversal rate in here that's, the order of a couple of reversals per million years. And then in the longer term, it looks like we see something where there are changes in reversal rate. And those changes in reversal rate, we all I think most people like to think of as being, yes, due to the thermal evolution of the core. And some of that is forcing, it's also about cooling of the core. So you could think of the core as forcing the mantle would be another way of putting it. But I think those are the long-term changes. And in that sense, they're like climate change. You could say climate change is actually being driven by internal variations if you think of the production of carbon dioxide as internal. So, it's all a matter of what you want to put in your Navier-Stokes equation, I guess.
Okay, thanks.
Thank you for your question. If there is another question on chat also. Well, I have a question. Maybe it's a stupid question, but I want to ask you if you think the different categories that you present for the reversal and the excursions, I think that it would be related also with the movement in the core, but do you think that it could be also different instead of the time? For example, if you think that it's a period that is cooling, maybe the category would be different instead of, or depending on that?
Okay, I think that's a good question, actually. We chose these categories based on the idea that based on this numerical simulation. And the thing about the numerical simulation is, even though it's 150 million years long almost, it's like 150 million years of the past 10 million years. Okay, so we're basically thinking of the simulation as being a stationary model, right? So we can get the statistics from it, and that that's kind of, I think, the strength of what we did in here, in that we have enough statistics to look at what's going on and decide on the categories. Now, it seems that the categories are pretty robust in the sense that you have to, the index depends on the strength of the field and the directional change or the deviation from an axial dipole. You could, I suppose, imagine that there could actually be a situation where you had a much lower dipole moment in the Earth and the directions were still stable. Because one of the things that we know about excursions and reversals is that we see that the field goes unstable when you get this big decrease in dipole moment. And right now the dipole moment's pretty strong, but you could imagine that there would be a time, it could be possible, though we haven't seen it, that there's actually a time when the dipole moment was much lower than it was today and we still got a stable dipole field. And that would be, you know, that might suggest that that there was less activity in the core, that you could still have a stable dipole field and not much going on, but maybe we haven't seen that yet.
Okay, thank you so much. And there is another question. Matthias?
Yeah, Cathy, maybe you want to comment on the because you're talking about the categories being robust, but I think we should acknowledge that the category 3 is pretty extreme, and you know, we categorize based on the simulation, which has a fine time step and a very high time resolution, but it might be could be pretty difficult to detect a category 3 event in
yeah, I should have said that actually. So if we go back to the very beginning of making these categories, if you look at this thing, we're talking about sort of 0.01% of what we see in here as being level 3. And if you think about the values of the dipole moment that you would need in order to get to level 3, based on just thinking about how the index is constructed, you would need a really low field strength in order to be able to detect this. And if you then think about what we are able to measure in terms of paleo intensity, I think it's pretty unlikely that we would detect something that fell in this regime from a real paleomagnetic record or in fact a paleo field model. And that's partly due to this inherent smoothing in time. It's also due to the limitations of our sort of ability to get paleo intensity records. Brendan.
Yeah, I had a sort of quick question about how this might change categorization of things that we refer to as excursions and reversals. So I don't know if you've tested this, but we have a lot of other excursions that are not the Laschamp, things that people call excursions that I think you've shown in your paleosecular variation index are more local. Do any of those show up as level 1 events, or are they all level 0? And then also the other question I have is, there are sort of things like, are there, for example, subcrons that people call subcrons that in this case would just be referred to as an event because the field is unstable throughout that time?
Short answer is, so far we've applied this categorization strategy just to paleo field models and global events. So we just based it on the dipole moment. So if you don't have a paleo field model, the actual dipole moment and dipole tilt from a field model. So if you don't have a field model, we haven't yet used this for this long simulation. Now, if we were to look regionally, which Stephen Mason has done in some of the lead simulations, then you see, he's looked at things where you just see a local event. So you see something where the index goes above 0.5 and then returns, but it's not seen everywhere across the globe. So that's an obvious extension for us to go and look within this very long long record and think about where things are starting and how they evolve over time. And that's kind of the nice thing about working with simulations is you can do that. To go to, you also asked about the level for what happens if you have something that's regional or a little cron. So you could, if you look at this definition in here, if you have something that is unstable and keeps going up and down below this 0.5 level, we count that as all part of one event. Now you could, that's our definition. You could, and I think some people would like to say that in actual fact, if you get something that looks like this, you've really got 1, 2, maybe 3 excursions in here. I would say that this is really just part of an unstable field value, as you said, and so that would be, and that's, I think, an interesting thing to investigate because, as you know, there are these things called cryptochrons where you can't really tell whether you've got a short chron or an intensity decrease. I think what this does is it allows you to think about the idea that associated with an intensity decrease, you get directional instability, and that might go on for a while, and the probability of a reversal occurring during that time is larger than it would be during a time when this index is lower. Does that answer your question?
Yes, thanks. It's really helpful.
Okay, thank you, Brendan, also for your question. And I'm not sure, it seems that there is...
Either I convinced them all or they're so skeptical they don't even want to say so.
So next MagNet will be on November 27th, and you will find all of the talks on MagNet YouTube channel.